So I'm going to talk today about the cosmic expansion hypothesis is falsified. The universe is not expanding. So I'm going to start with a methodological question or statement. The scientific method is the method for making accurate predictions. The sole scientific test of the validity of hypotheses is comparison of predictions with subsequent observations, not observations made before the predictions are made, but made after. It's a very important point. The predictions of the cosmic expansion hypothesis have been consistently contradicted by subsequent observations, while those of the non-expansion hypothesis have been consistently correct. Therefore, the cosmic expansion hypothesis has been falsified and must be abandoned. So I hope to show some of the reasons why this is true. So I'm sorry, I have to correct something here. So the Tolman test is one of the clearest yes-no tests of the expansion of the universe. If the universe is not expanding, surface brightness is a constant with distance. That is, an object that's twice as far away, its apparent luminosity goes down by a factor of 4, and its apparent area on the sky goes down by a factor of 4. Surface brightness is defined as the ratio of those two numbers. That is, apparent brightness divided by apparent area on the screen. So it's a constant if space is not expanding. If space is expanding, surface brightness, defined again on the basis of per unit frequency, or AB magnitudes in astronomy speak, goes down as 1 over z cubed. Why is this the case? Well, one factor of 1 plus z comes from the stretching of light due to the stretching of time from the expansion of the universe. 2 additional factors are from the expansion of the angular diameter. Now, people have commented on this, but I just want to say briefly, this is a necessary consequence of the expanding universe hypothesis. If the universe is expanding, the galaxies were closer when the light is emitted. They're now further away. And therefore, the difference is the difference in the apparent angular size. So the prediction in the Big Bang, or any expansion, whether it's Dr. Gupta's slower expansion or the regular 13.8 expansion, is that there is a minimum to the angular size, and then the angular size begins to expand. If there's no expansion, then of course, as in space here on Earth, the angular size drops without limit with increasing distance or with increasing redshift. The observations already made before JWST with HST completely confirmed the constant surface brightness. So we're here in previously published papers comparing the radius of an object that are constrained by having constant absolute luminosity. So if you look at the radius of an object which has constant luminosity, then that's exactly the same as looking at the surface brightness. And there was no variation both with our data, which was the blue dots, and ours is myself, Cardo, and Renato Falama, and also with the red dots, which was Shibuya data. This was based on the assumption, the hypothesis, that distance varies proportionately, linearly proportionally to z at all z, which was the hypothesis not based on theory, but based directly on observation. That allows you to determine what the absolute magnitude of a galaxy is. Surface brightness is a directly measured is a direct measurement on the images, but to look at what is the luminosity of the galaxy, you have to have a distance formula. So we hypothesized that, and we got a very close correlation of surface brightness with constant. So the prediction was verified. So what do the JWST observations show? Ricardo and I published online a paper saying they would show the same thing. So we've just been able to test whether that prediction was true. So the data we used was from the Morishita paper, which was 339 galaxies in this redshift range. And we selected within that 69 galaxies that had spectroscopic redshifts, because there is some evidence that there are systematic, small systematic errors in the photometric redshifts with JWST. So to avoid those errors, we just used the spectroscopic. Now, they used a different measure of angular radius, a different method than we did. So to be able to compare our data with our earlier data, we remeasured 24 JADES galaxies that they also measured to derive a conversion formula. And we found that there was a tight correlation between our measurements and theirs, but it was a nonlinear relationship because we were measuring them in a different way. And Ricardo will give a short presentation after mine on exactly how we are measuring the radii of these galaxies. So since the most distant galaxies had luminosities, absolute luminosities that did not overlap the closer ones, we used the correlation between surface brightness and absolute magnitude. That is, brighter galaxies are bigger than smaller than dimmer galaxies. And we compared that surface brightness to magnitude relationship with the prediction that if surface brightness doesn't change, that relationship would not change at any redshift. So in order to compare distant galaxies with very near galaxies observed by different telescopes, you have to match the resolution of the telescopes. So we're comparing galaxies in the very near universe measured by Galix, in the intermediate universe by HST, and in the most distant universe with JWST. So we matched these so the minimum linear radii that each telescope could observe are the same. So from the observed resolutions, we come out with these ratios. And we also matched the wavelength rest frame bands to NUV or FUV. So what did we find? Well, when we looked at the nearest group, which was from the Z to 5 to 6, we saw no change in the surface brightness. Now here, the blue dots are Galix galaxies at very low redshift. The red squares are the JWST, just measured galaxies, at a redshift of 5 to 6. And HST are intermediate Hubble galaxies. So I want to draw attention to the blue line and the red line, which is the correlations, the observed correlations of surface brightness with absolute magnitude of the galaxies. And obviously you can see they are very close. In fact, they are statistically indistinguishable. And as we go to higher redshift, this is a redshift of 6 to 7, looks even better. 7 to 8, we lose the overlap, but obviously correlations are nearly identical. And at the highest redshifts, 8 to 10, they are identical. So the question here is observationally answered. not only in 2 dimensions, which is surface brightness versus redshift, but in 3 dimensions, surface brightness magnitude correlation versus redshift. And the prediction of the non-expanding hypothesis is completely confirmed. If we put this data together with the previous data, we see that there is no change in surface brightness all the way from a z of 0.0027 to a z of 10 over a factor of almost 400. And of course, this contradicts completely the prediction of the expanding universe. So if we put the expanding prediction interpretation of this data, this would assume that the surface brightness of the galaxies observed is really 7 magnitudes greater than the surface brightness of the near galaxies. Statistically, that's 36 sigma away from the actual observations. You have to explain this difference ex post facto after you actually know the results by an evolution of galaxies such that each individual galaxy must at every redshift evolve by the exact amount necessary to go from the red line to the blue line. I would contend that such a hypothesis is not a scientific hypothesis, but a pure ideological hypothesis. But we don't have to question whether this is in any way physically possible, because we have an independent measurement of radius. We have data from ALMA. The spectra from ALMA show the gas mass, which can be determined by the amplitude of the spectral lines, and the rotational velocity, which can be determined from the width of the lines, independent of whether there is expansion or not. From Newton's laws of gravity, we can get a minimum radius that these galaxies must have. If we compare the minimum radius with the radius that is predicted on the basis of the expanding universe model, we get that the predicted radius is between, which are the blue dots, is between 3 to 10 times less than the minimum radius as independently determined from the ALMA data. In all cases, the non-expanding radius is approximately 2 or 3 times greater than the minimum radius. So these impossible galaxies, different ones from the impossible early galaxies, show that expansion is impossible. It's physically and observationally contradicted. Now, it's not as if this is the only contradiction. I have to respectfully disagree with Leandros, pardon me, because there is not a good agreement between the predictions before observations of the expansion model and any set of data except the deuterium abundance. 16 separate sets of data are contradicted. I can only go into a few given time restrictions. The lithium abundance is predicted by the Big Bang predictions or any expanding universe predictions that leads to hot dense in the area shown by the red lines. The observations of older stars in our own galaxy are the blue dots, and the blue dots descend with decreasing abundance of iron, which is a good measure of how primordial in our own galaxy these stars are, towards 0. And at the moment, the data is about a factor of 20 below Big Bang predictions. So not a good agreement at all. The predictions for the far more abundant helium are also too low than the minimum predictions of the Big Bang, which are the red lines. So these are stars that are quite local to us in the galaxy, and they show helium abundance that is much lower than predictions. Throwing out data, which is what a lot of the cosmologists are doing these days, doesn't even help this. This is a measurement of extragalactic ionized gas, and this paper actually shows that observation is below the predictions from the Big Bang, but it's only within range because they throw out all of the data with the lowest helium abundance, which are these open dots. The cosmos is not homogeneous. Francesco has referred to this. Large-scale structures that are far too large to have formed in less than 100 gigayears have been observed in many different sets of data. The cosmos is not isotropic, which is a second vital assumption of the Big Bang expanding universe hypothesis. This is a very recent paper from October 20th of this year, and from a different paper, this is the variation in the observed value of the Hubble constant, depending on the direction we look at in the sky. This is not all, and this was from the table of contents of a giant paper written by hundreds of authors that show all of the contradictions or many of the contradictions to the LCDM. In no case are the predictions correct. Over the past 7 years, we have the development of what's called the crisis of cosmology, but is really a crisis of the Big Bang. This is a plot of the number of separate data sets, not separate papers, but separate data sets that at that year were in agreement with Big Bang predictions. And the red line shows the number of separate data sets that showed the Big Bang was wrong. And you can see that since approximately 5 years ago, the number of wrong predictions has rapidly been growing, and the number of right predictions has declined to only 1, which is, as I say, the deuterium abundance. Well, if the Big Bang expanding universe hypothesis is junk, then the evolution of the cosmos can be understood using basic concepts of gravity, nuclear reactions, and plasma physics. And importantly, imitating these same basic plasma processes that we learn about by studying the universe is the way to produce fusion energy here on Earth, which is what the company I work for is about. These basic principles have been developed over hundreds of years from experiments here on Earth. One of the most basic principles is the pinch effect. This is the effect by which currents moving in the same direction produce magnetic fields that cause them to attract. Magnetic fields can be attractive, while currents moving in the opposite direction cause currents to repel. Even though this pinch effect is not familiar to many astrophysicists, it's basis to all of our technology in developing fusion. The pinch effect leads to the formation of force-free plasma vortex filaments, in which the current is constrained to move in the same direction of the magnetic field lines. There's a basic secret of the universe, because the formation of these plasma filaments, together with the gravitational force, is how structure forms. We observe filaments at all scales in the universe governed by the same plasma physics laws. From our experiments in LPP fusion, in which the filaments are on millimeter scale, up to star-forming clouds on parsec scales, up to galaxy-forming filaments, which have been observed in other clusters of galaxies. These filaments are on the scale so that the letter E is almost exactly the same size as our Milky Way galaxy. And we see filaments on even larger scales on superclusters of galaxies. These filaments, we can go into in the discussion, have to be formed with the interaction of electromagnetism and gravity. They cannot be formed by gravity alone. JWST has shown the hierarchical fractal nature of these filaments, for example, in nearby galaxies like M74. In 1989, I developed a plasma model that used these theories of structure formation to predict the formation of light elements, not through a Big Bang, but through the origin of stars much larger than the sun that burn helium far faster in the early days of each individual galaxy. They produce deuterium and lithium through cosmic rays, and I published correct predictions that were validated subsequently of helium, deuterium, and lithium. And this is a little simulation of a spiral galaxy forming through electromagnetic forces alone. The cosmic microwave background with no Big Bang derives its energy from helium production. Has been noted for decades, the amount of energy necessary to produce the helium we observe equals the amount of energy in the cosmic microwave background. This energy coming from stars is thermalized by dust to 20 K. But how is it thermalized and isotropized down to 2.7 K? Well, we know from both observations in the astrophysics and observations in the laboratory that filaments form plasmoids, which are self-contained, magnetically confined objects. And these plasmoids, by known processes, emit high-energy beams of plasma, which form filaments throughout the universe that can scatter microwave frequency radiation. And this theory led to a prediction back in the 1990s that if microwave radiation is being scattered in the local universe, then as in a fog, radio radiation would fall with distance more rapidly than infrared radiation, which could penetrate this fog. And that's exactly what has been found and was published back in the 90s and has been confirmed since, that in the local universe, this is up to the order of 100 megaparsecs, where evolution is not a consideration, we find that the radio radiation for galaxies with constant IR radiation falls rapidly with distance from us. And assuming we are not in a special location, that can only be because the universe is not transparent in the microwave radiation. It's translucent. And as physicists know, if an object is sufficiently opaque, it will produce a black body radiation. These filaments that I've been talking about are vital to our own technology. Understanding them is vital to producing fusion and producing our goal, which is a cheap, clean, and compact source of energy. So a word from our sponsor. But these cosmological debates do matter for us here on Earth. Now, why has the Big Bang, which has no scientific support in observations, still survived so long? Part of it is what we call the emperor's new clothes effect. In other words, if in academia you say the Big Bang did not happen, or you shed doubt on the Big Bang, or that expansion did not happen, you are considered to be stupid or unfit for your job, and you won't get any funding. Since the funding is controlled by people whose entire careers have been devoted to the Big Bang expansion model, this has an inhibiting effect. And I completely agree with Rajendra that publicity about other alternatives makes people more willing to take risks and study other alternatives. But in addition, and this is very fundamental, there is a methodological problem with conventional concordance cosmology. The method of the Big Bang is the Ptolemaic method, not the scientific method. In the Ptolemaic method, Hypotheses come from unquestionable assumptions, such as the universe is homogeneous and isotropic. These assumptions lead to wrong predictions, but after wrong predictions, the theory is modified to fit previous observations. So theory comes after observation and is not tested by observation. In the scientific method, hypotheses are derived from observations. They are accepted only based on correct predictions, about the future. Ultimately, they become the basis of new technology, because science through technology allows us to predict the future and therefore to control our own future. The method today used of simply adopting new hypotheses to fit previous observations is not the scientific method. This is not science. This is the Ptolemaic method. This is demonstrated, for example, with this rejection notice that we got from Nature. The question in the title, will LCDM cosmology survive the James Webb Space Telescope? We wrote this before JWST. Plainly has the answer, no one knows, since there is yet no data. In any event, the authors claim at the end of the abstract that they already know what JWST's data will be is plainly unscientific. This rejects the basis of science. This rejects what makes science useful to us, which is the ability to predict observations before they occur. These methodological errors are not new. In 1937 in Nature, Dr. Herbert Dingle wrote an article called Modern Aristotelianism in response to the development of Big Bang cosmology, before it was even called the Big Bang. Simply making assumptions, which by now have become dogmas. It's assumed the universe is homogeneous. Why? Because the possible alternatives must be ignored if we are to make our speculations definite. It is assumed the universe is isotropic for the same reason. Making assumptions because they make our calculations easier is not scientific. To summarize, the expansion theory prediction is contradicted and the expansion is not occurring. Thus, there was no dense period of cosmic evolution, no Big Bang. The redshift distance relation is not caused by expansion, but by something else, we don't know what else, that occurs to the light as it travels. Without expansion, the evolution of the cosmos can be correctly described using known processes, gravity, electromagnetism, and nuclear fusion. So thank you very much. And before we have questions, I'm going to turn things over to Ricardo, and he's going to give us short presentation on how we measured the galaxies, and then we'll have questions. And after that, move into the general discussion.
So this is a work I'm making with Renato Falomo, and of course with Eric Lerner. Okay, we're using the James Webb Space Telescope, limited to the JADES NIRCam program. This is done simply because this program was so kind to make the data available online to the community. So the reduced data are freely accessible. Data are available in several filters. You can see the list here. There are almost 15 filters. And we focus only on two ones. The F150W, 150 means it is 150 nanometers, is the central wavelength, and is a wide filter. And then the 277, which is 277 nanometers. again wide. This is appropriate for redshift 5 and 8 or 10. In doing so, we started from a list presented by Morishita et al. And they selected a galaxy from this image and from the JADES data according to the Lyman alpha dropout technique and or fitting the spectral energy distribution built with this set of filters, not from spectroscopy. And they extracted a sample of 110 galaxies, which were really appropriate for our purpose because they were covering the range from z = 5, that was matching the highest redshift we could probe with HST, and extended to redshift 10. And by the way, Morishita et al. Did present also magnitudes and radii for all the sources they selected. So basically the work was already done, but we had to double check that everything was okay. So we had to remeasure all the galaxies. And first of all galaxies were individually inspected to great detail because, as I will show in a moment, there are many galaxies which have disturbed morphology, and these have to be eliminated. Then we extracted the radar profile for the isolated galaxies, and from this we derive a magnitude, which means a total flux from the object, and a radius to derive the size. Okay, this is an example. This is just a small part, about 1/10 of the entire JADES field, the big image on the left. And you can see there is a red square, which is zoomed on the upper right corner. And again, is zoomed to highlight the central galaxy that you see there. So you see, there is one important thing you can already see here. So distant galaxies are seen small. This is a blatant contradiction to what we expect. Of course, you can imagine distant galaxies are intrinsically extremely small. So to compensate the limited angular size distance that is computed for them. But of course, this is a quite weird hypothesis. The direct observable data is that distant object keeps getting smaller and smaller as their distance increases. And this is a direct observation. It's a matter of fact. There's no question. Okay, these are then a contour plot for the same galaxy we just saw on the previous slide. You can see the F277, the F150, the two filters, and you can see the contour plot. Actually, in the F150, which has shorter wavelengths, so the diffraction limit of the telescope is smaller, you can see it slightly better. So this is a small extension on the left, this object, that is almost gone on the 277 filter. But this is a good target, and this was retained actually in our analysis. Look at the scale, 0.5 arc seconds. So the object is completely contained in a very small region of the sky. These are other examples. These are two disturbed galaxies. The one on the left, marked as 0, is a C = 8 galaxy, and you can see this a clear extension possibly is double. So there is one important, I mean, at the center, there is the target, the one is that has been selected by Morishita. And on the slightly on the left, you can see there is an extension, possibly a second galaxy, a companion. On the right panel, you can see at the center again the selected target, which is the image is affected by the presence of a nearby companion, which is most probably a foreground object, but this one is covering the distant galaxy. So extracting a radar profile here becomes quite difficult. This is another example, and this is clearly, well, affected by, again, a nearby companion. You have at the center of the image, you have the selected target, and on the upper right, you have a companion galaxy. So when you extract the radar profile, which is extracted on increasingly larger circles, you see that initially the slope is decreasing because the central point is at the center of the target. It's placed at the center of the target. So then it is decreasing, but then eventually it starts increasing because the contribution from the other companion becomes relevant. You might want to notice here that we measured an alpha light radius, which is about 0.2 arcseconds, pretty big because it is taking into account also the companion. So this object was rejected, of course, later on in the analysis. And look at the value on the top of the plot, the REC, which is extremely small. This is indicated by the red dot dashed line at 0.001 or more or less. That is the value that Morishita assigned to this galaxy. And this value, of course, is completely inappropriate to describe the object. Most probably, the software that they used was fooled by the presence of the companion. I don't know. We have no idea what happened there, but certainly the radius that they quote is inappropriate to describe this object. So over here, we have another example. We have on the left 4 good target, isolated, without any nearby companion. So for this one, you can extract the profile that we will see in a moment, and the results are extremely good. And while on the right, you see object with problems because of nearby companion or double morphology and so on. These are a few examples. Again, the 4 objects we saw before, and now the radar profile. Here, first of all, you can see the profiles. The dots follows very well a straight line. This is a log plot, so you expect this for a disk galaxy. All the galaxies we measure are fully consistent with the disk, and which is okay. These galaxies are the most common galaxies, so it's logic to find them. And in order to assign an effective radius for this object, we decided to follow this strategy. So we first excluded the first 2 points of the profiles because those are affected by the smearing of the point spread function. So the first 2 points are excluded. Then from point 3, we start computing the slope from point 3 to point 4, then from point 3 to point 5, point 3, point 6, and so on. So we end up with a series of value for the slope. And then we take the median. And this ensures that if there are some deviating points, the the media will exclude them, and we will end up with a correct representation of the radius. Again, look at the object indicated with the number 18 in red. The effective radius that we measure is about 0.1 per second. And for the same object, the Morishita value, the one above in the plot in brackets, is 0.019. So it's 0.02 basically, almost 10 times smaller, actually 5 times smaller than what we measured. But you see the vertical red line shows you the value. And this is totally inappropriate. You cannot describe that object. It's way too small. So we really don't understand what they did. But certainly our values are fully capable to describe these objects. And so we are confident that our results are good. This is one example, for instance, of another object that had to be rejected because of the presence of an extension on the lower right. But even in this case, the fact that we are taking the median slope computed with this trick, so moving from the third point to all the others, so the profiles will start increasing after 0.2 seconds, but this is cut out by the median, by the computation of the median, and so we end up with an alpha radius which is actually capable to describe the object, and nevertheless this one was excluded from the sample. So I end up here just saying that there were 110 galaxies selected in the ratio range from 5 to 10 in 2 different bands. We had 81 which were appropriate for measurements, and in the F277W filters, and 66 on the other. On the other end, Eric decided to focus only on objects with spectroscopic redshift, which was a good decision, of course, because they are more reliable. And as you saw, the results are pretty striking in the sense that we find no evolution on surface brightness. But again, the striking result is that these objects are extremely small. So we have massive galaxy observed to be small, which means that we have a blatant contradiction to what lambda CDM is predicting. But this is in full agreement with the Euclidean non-expanding idea. And I stop here. Thank you.
Okay. Thank you very much, Ricardo. Before we start questions, I just want to make one clarification for non-astronomers in the audience, is that the method that we arrived at quite a few years ago, this fitting of this curve, is based on a very convenient fact about disk galaxies, that their brightness descends with radius exponentially to a very good degree. So if you measure this exponential curve, which you plot it logarithmically as a straight line, you can get a very good measurement of their radius. If they're elliptical galaxies, it's much more complicated. But fortunately, most of the galaxies that we observe are disks, so that's what we've done. All right, so first we'll take questions for Ricardo and I, and then After 5 minutes, we'll launch into general discussion among the presenters.
Very impressive work you have presented. Congratulations to you, Ricardo. My question is, have you submitted to some journal any reaction yet?
No, so far we haven't prepared a paper. The data are pretty new, and you are actually the first one to see them.
To be specific, Ricardo sent the latest version of the data to me, I believe this is Friday, Tuesday.
Yeah, a couple of days ago.
Yeah, so yeah.
But
This is
I'm
definitely
sure
its
Eric
debut,
will quickly
and
prepare a draft.
We definitely will prepare something. We hope for publication in a prominent journal. We'll see.
We do things, we do measurements the old way. I mean, we take every object individually and we carefully fit it. On the literature nowadays, you see almost systematically huge list of measurements which are made automatically without checking the actually the input data, and this leads, in my opinion, to a lot of spurious result, if not to say completely wrong. I show you a couple of examples of the values quoted by Morishita et al. They were completely inappropriate. I don't know what they are doing.
Well, I certainly, from their paper, they are attempting to model the PSF. That's the point spread function, which blurs the image. And unfortunately, that's really a wrong approach, because we're taking advantage of the fact that JWST and HST before it are very sensitive and can trace the light of the object way out into its outskirts, where we can use this straight line exponential fall off. However, as I showed, there is a clear correlation between our results and Morishita's results, even though for individual galaxies, they're quite different. So they are measuring something that's related to the radius, but clearly what we're measuring is the radius of these exponentially falling disks. But I also want to say that this whole question of isolating galaxies is quite critical, because galaxies, unlike stars, do not live in isolation, especially not in the sky where we have projection of foreground. And this is clearly the origin of what we call the resolution effect, which is in nearby galaxies where we know there's no evolution. Galaxies that are more distant appear larger just because their neighbors are too blurred to see them. With high resolution, we can see that there's a neighbor. With lower resolution, the neighbors just get blurred into the image and make it look like they're larger galaxies. So, Lewis?
You mentioned earlier, Eric, that you have a cutoff for the angular size of the galaxy, or not the angular size, I think the real size, so that you have galaxies that all have the same size independently of the redshift. Isn't it? Did I get that right? Or
the observations have a clear cutoff at the lower end of the angular radius.
okay.
So it's clear that this is observational due to the resolution of the telescopes. For one thing, I can't show this to you, so I'll have to use my hand. The intrinsic variation in the distribution of the galaxies with sides sort of looks like this, and then it cuts off very suddenly. So that's clearly observational, cutting off a more gradual drop. And second of all, in all three telescopes, the ratio of the minimum radius observed to the pixel size is almost identical. It's all between 1.5 and 1.7 pixels, which is reasonable, obviously, if the galaxy's true radius is significantly under a pixel, the fall off is going to be too great. So this is not something that we're imposing on the data. This is something that the telescope's resolution imposes on the data. So what we're doing, and this does use the model. So we use the model of matching the linear dimension of the galaxy using the linear relationship of distance to z. That allows us to get that very close match between the surface brightness of the far and the near. If you use a different relationship,
perhaps you are not answering the question.
I'm sorry?
It seems to me you are not answering the question. He wanted to know if we are somehow limiting the size of the galaxy we are studying, so to have always the same size. But this is not the case. We only have a limit on the lower size because there is a physical limit, the diffraction limit of the telescope. And this is why in the plot that Eric showed, at the highest Resi, there was no longer overlap, because at the highest Resi, we see only galaxies which are larger and brighter than the one we can see Resi 0.
That's right, yeah. No, I get that. So
in that direction, there is no limit, no restriction.
But so for galaxies that are smaller in angular size, what I'm thinking about is the real size, the linear size, the actual size of the galaxy. Those that are far away, like the observations will eliminate the smaller ones that have a real linear size.
Basically, there are two ways of dealing with that. One is, and we did this in detail with the HST, we have not had time to do it with the JWST, is that we plot the distribution of the galaxies and show that the distribution intrinsically has fallen off before we get the cutoff that's due to the resolution of the telescope, so that it's not biased. So you can see that fairly clearly, for example, in the Gaelic sample. You can see that as we're going to lower numbers in the surface brightness, that's going to lower radii. So when you get down to around here, that's when you're getting to the cutoff of the resolution of the telescope. But you can see that the vast majority of the galaxies are bigger, and therefore the actual distribution has already fallen off. And I'm sure we'll find the same thing with the JWST galaxies. What this basically means is you can't indefinitely extend this comparison. So even with JWST, if you go up to the maximum redshift that JWST can reach, which is already demonstrated to be around 15, this cutoff will be cutting into your distribution. So you're going to be getting somewhat of a fall off in accuracy. But there is a second way to address this, which is to use the median surface brightness. Because if you know the number of galaxies that are unresolved, and in this particular sample, Morishita, we don't, but in future samples, I'm sure we will, then you can simply get the median by counting the unresolved ones as being smaller than any of the resolved ones. So you can still compare median surface brightness, but we don't have to really do that because we've still got resolution to spare in the range of by going up to 10. So that's basically the answer, that in this range, the telescopes are really seeing the entire sample.
So I think you were going to answer, like I had a follow-up question, is you use the linear redshift distance relationship to, if you try to use the LCDM relationship, how does that change your analysis?
Well, you have to realize that these are
I mean, it's probably going to go off completely and not work at all, but
basically what we're talking about, this resolution effect, is an effect that is of the order of 0.5 magnitudes. So that if we go from the farthest Gaelic samples, and again, the Gaelics are low redshift where we know there is no evolution, there's nothing except observational effects. If we go from the farthest Gaelics to the nearest, the surface brightness changes by about half a magnitude. When we go to the expanding universe model, the vanilla LCDM, you've got a gap of 7.5 magnitudes. So that's hugely an order of magnitude different. So the resolution effect is essentially not relevant. And even if you use, now I will qualify that I'm not quite sure I know of Regender's formulas, but if you just cut the redshift effect in half, because only half of your redshift is due to expansion, you still have 3.5 magnitudes, which is way, way outside the any of the observational uncertainties. And if you go to non-expanding universe and you go to the logarithmic distance formula, and you still have about 3 magnitudes difference. So you've got these very large differences that can only be explained by some hypothesized, and I'm afraid to say, but I would have to say completely ad hoc, post hoc evolution of size that precisely retains the slope of the surface brightness to magnitude relationship. So the effects that we're trying to correct for to measure small differences in surface brightness just are irrelevant to these very large shifts that occur if you use different hypotheses for explaining the redshift.
Eric?
Ricardo.
Yeah, I just want to add that in this particular plot, you see the values that you would expect, but this is not what is observed. If you, Eric, go back to the previous slide, you see that the surface brightness for the nearby and the distant sample is the same, and that is a direct measurement. There is no cosmology involved there.
Right. Again,
the luminosity divided by the surface of the object.
I completely agree. That point has to be emphasized. The surface brightness is directly measured off the images. Now, there are variations in how you measure it, which Ricardo was pointing out, but they are not dependent on your cosmological assumptions. What this plot is the Big Bang interpretation of the results that this would be the surface brightness as observed at the object, because in order to interpret the actual results which show no surface brightness, the Big Bang expansion model has to assume an exactly counteracting increase in surface brightness. So again, surface brightness increases in the downward direction. Maybe I shouldn't have done it that way, but that's how the numbers run. And this basically hypothesizes that these are far, far brighter galaxies, thousands of times brighter. And as I say, that hypothesis is really completely unscientific, because it means that every galaxy has to evolve according to a strict schedule in which they, like a railway, follow what is necessary to counteract the imaginary.
Can you go back to the slide
brightness.
where, like, it's 8 to 10 redshift, but with the static universe, not expanding universe?
Okay, this is not with the static, this is actual observation.
This is not expanding? Okay.
This
So
is actual observations,
yeah. So
the
my
assumption,
question is, for this is, if you look at the red dots, these galaxies have different actual sizes, right? 10 kiloparsecs or something.
These are bigger than the local ones.
These are bigger. Yeah, okay.
The thing
So
is
the local ones,
smaller than
the local ones are smaller. But if you select out of the local ones, the big ones that have the same, roughly the same range in size as the red dots, which one would be left on this plot?
now, again, we're not selecting these. The observations are selecting.
No, you're not. I know you're not, but I'm asking if you were selecting, what would happen? If you were selecting galaxies that have the same size.
Look, we can't dictate to the universe.
No.
Although,
but you can dictate to the analysis, though.
all right, so so what we have is this relationship between surface brightness and absolute magnitude. If you converted this into radius, what it would show is that the radius varies slowly with brightness. So the surface brightness is very dependent on the brightness of the galaxy, the intrinsic. But the radius of the galaxy has only a low dependence. It's maybe something like 0.2. So the radius of the galaxy is to the 0.2 exponent compared with the brightness, the luminosity of the galaxy. So that's what we're seeing. What I'm emphasizing here is there's a very tight relationship. And this tight correlation between surface brightness is extended. The reason we don't have any blue dots way out here is because we're sampling these are very rare galaxies. These are galaxies that are several times brighter than our own Milky Way galaxy. And we are sampling a much, much smaller volume with the blue dots, which are close to us, than with the red dots that are distant to us. Now, the blue dots, I should say, are from a greater part of the sky, much greater part of the sky than the red dots. But we're still, that doesn't make up for it. We're still sampling a much smaller volume. So these red dots just don't exist in the local universe because they're too rare.
Yes, I understand all that. My question is, these red dots are galaxies that have a physical size that is much bigger on average than the blue dots.
They're much brighter than the blue dots. As I say,
but what about the physical size? They're about the same size?
They're somewhat larger because the dependence of the physical size is approximately the luminosity to the 0.2.
That's right.
So if you go from 19 magnitudes to 22 magnitudes is 3 magnitudes, which is 10 to the 1.2. So 10 to the 1.2 times. So basically, you've got the biggest galaxies are about 70% larger than the biggest ones we observe here. So they're not grossly different in size.
What I'm trying to say is, what I'd like to see is a comparison of galaxies as you've done now, but also add the restriction that you want to compare galaxies that have the same physical size. So that would remove some of the blue dots. Like there's a range of size that you have for the red dots. Use the same range of size for the blue dots. It might not change anything, but I'm just wondering what would it do?
You see, if you focus on a specific absolute magnitude, for instance, minus 19, then you have blue points and a couple of red points. Okay, here any variation in surface brightness correspond to a variation in size, because if you fix the luminosity, then the size have to change in order to have different surface brightness. In this case, the blue dots are lower. Some blue dots are magnitude minus 19, are lower than some red dots. So those galaxies are actually bigger than the one from the James Webb data. So the near galaxy are actually bigger than the distant one.
Okay.
But I mean,
Okay.
as I say, this is very new data for JWST. It's only a few days old. But if you go back to the HST, we actually did analyze it both as radius as well as surface brightness. They are basically mathematically equivalent, because if you take a sample of galaxies that are the same luminosity, and if you measure their radius, you're measuring their surface brightness, and vice versa.
That's in the non-expanding universe.
Also, Luis, there is an important point to make here, because the size of the galaxy is specifically what you want to derive. If you use the cosmology to force the galaxy from different samples to have the same size, then automatically you will end up with the same surface brightness. This is an error that I made at the very beginning, and an error that is made quite commonly.
Yeah.
So if you start saying, no, I want only to consider a galaxy of the same size, when you do that, you are already assuming a cosmology, and so your test is no longer valid.
Right, and the difference, good point, Ricardo, and the difference with looking at them versus absolute magnitude is that the absolute magnitudes don't differ in the two models. I don't have the graph available, but the linear model fits the supernova data perfectly, because mathematically there is almost no difference until you get to very high redshifts between the linear model and the lambda CDM model, except that the lambda CDM model has 2 extra free variables. So if we're comparing magnitude versus magnitude, we don't have to specify the cosmology. As Ricardo points out, if you compare size versus size, then you get into circularity, because that's exactly what you're trying to determine.
Sure. That's,
again, the surface brightness, which is a direct observable, is the easiest way to go, because the prediction of non-expansion is simple, that there's no variation, and that's what's confirmed.